Welcome, Hen. How are you, Hen? Oops.
Hi, good morning. How are you? Good
Good.
night, or
Where else are you calling in from today, Hen?
I'm calling from Tel Aviv, from
From
Israel.
Tel Aviv. So it's a
Yeah.
more reasonable time there, but still never reasonable, right?
It's 7:45. That's
Yeah. And so you
and
work at Epsagon, or also a sponsor, I believe, right?
yes, we are also
So
sponsoring.
thank you very much for your support. Please, everyone, do check out everything that Epsagon do with their observability around microservice environments. So that's awesome. And you're a solutions engineering lead there.
Yes, I'm running the solution engineering team in Epsagon.
That's awesome. That's awesome. Good to hear. And
Thanks.
what are you going to be talking about today then? Error handling in stateless environments is the title. What are you going to be talking to us in
Yes.
more depth about?
So basically, I'll just go over through all the different types of errors that are possible in stateless environments, specifically in serverless. And we'll just touch a little bit of some of the techniques on how to actually improve the way that you're handling errors in those environments, and also a little bit about distributed tracing.
Mm-hmm. Sounds good.
Yeah,
Well,
hopefully
let me pull your screen in and we can get going. So we're limited on time. So I'll pass over to you, Hen.
Thank you so much. So thank you guys for joining me, and I'm going to talk about something that is important to all of us. Which one of us didn't have any production error this week? I'm guessing most of you did. So we will just cover up the different types of errors in a stateless environment, and also the techniques on how to actually overcome them. But let me just first introduce myself. My name is Hen Peretz. In the recent years, I've been working close with probably the most dominant stateless environments today, which is serverless. And I've been running the solution engineering team in Epsagon. And I'm also a fresh dad. I have a young daughter. She's 18 years old. Her name is Yuval. Basically the reason that I wake up in the morning. And I'm calling you from Tel Aviv, Israel. So today we're going to discuss errors in the stateless environment. We're going to focus on retry mechanism and try to share how to implement distributed tracing. Distributed tracing for me is just the key to gain full observability into distributed systems. So just first thing first, let's talk about errors in the stateless environments. Everybody got them. Despite of some stateful environments like you used to have, stateless environments are much more related, or errors are much more related to the actual environment where the code actually runs, rather than just a logical error, meaning that a stateless environment is not affected by the actual state. It doesn't affected by customer that is currently querying my services one by one, but it's just being affected by the entire environment as a whole. The first example I'm going to use is a simple application utilizing the most common stateless resources out there. This application consists of 4 different stateless components. We have basically customers that are streaming events through API gateway, which is the HTTP endpoint, into a Kinesis. And Kinesis is probably just used to get a fast response back to the customers, but it's also used for batching. And this Kinesis is triggering Lambda functions in order to perform some sort of data enrichment, and saves it all in DynamoDB. Just by looking at this architecture, I'll probably give it 9 or 10 at the rate of being fully stateless and fully serverless. And we might think that customers cannot really affect each other because there is no state, but a lot of customers can actually, once they stream a lot of events at the same time, a lot of things can actually go wrong in all of those components. I'll just try to touch one of the most main ones. So a Kinesis can be overloaded if we don't have enough shards. And the main way of actually solving that is to manually adjust the number of shards, which is not that trivial if you guys already experienced that, because you can only adjust shards a certain amount of time in a day, so you need to be very calculated about that. But a much more broad solution with that will be to spread the partition keys range rather than just drawing out shards. And I think the best way will be to just implement automatic shard scaling, which hopefully one day AWS will just have that built in and you don't have to build it on yourself. And even a Lambda function is not prone to errors. So a Lambda function can suffer from exceptions and out of memory and also timeouts. And unfortunately, I can't give you any tip to actually stop exceptions rather than just write better code. But you can also manually adjust the duration to reduce the timeouts and also adjust the memory in order to have less out of memories. And even just catch your known exceptions and not actually break when something happened. And the same goes for DynamoDB. As for DynamoDB, the most common errors are involving the traffic handling, meaning that it can reach its read or write capacity limits. Luckily, AWS already offers auto scaling, so we don't need to deal this scaling down or upscaling. But just take in consideration that without any hard limit, this can get very pricey. So this is just the tip of the iceberg when it comes to possible errors and in a stateless environment, and the list just goes on. And there's just other services also to consider. So Elasticsearch or Athena or Firehose or RDS, for example, all have their own limitations and configurations that actually affect the service's behavior. You need to have code that is prone and aware of all the possible errors, but not even errors, you just want to identify issues before they actually happen. And there's a lot to do when you reach a connection limit in your database. There's not a lot to do when you reach a connection in your limit in your database, but it will be extremely useful to identify a slowdown in your application. So this will eventually lead you to actually finding the root cause of the problem. So basically, this just led me to a technique called middlewares. And middlewares is basically using middlewares. It's pretty useful to try to identify and handle errors in a stateless environment. And the middleware just acts as a layer before and after the request that is being handled by the service. And it can be used for various of operation like capturing and enriching exceptions data, and also measuring the total duration and much more. One of my favorite open source library that actually allows easy middleware implementation is MIDI. And this is just an example of how to use MIDI with AWS Lambda. It's also written in Node.js. So MIDI.js is probably the most famous middleware library in JavaScript. It's, for me, what it wins is that, what wins for me in that library is that the ease of use. So it's pretty easy to implement middlewares and also add a couple of middlewares on top of one another without actually having to change your code a lot. In this example, we have a process payment that is actually just our handle function, and we use MIDI to add layers of logic. So the first logic is every time there is a request from the customer side, we can take that request and add, for example, an event logger that will log the event data, or use a timer to tell us how much time this request actually took. And just by taking this information, we can later on either we parse it from the logs or parse it from using a distributed tracing agent, which I'll reach out across the end of the lecture. You can take all this information to gain some more logical data about what's actually going on in this distributed system. And sometimes our application can just get malformed data, and we don't want to just recover from that case, but we want also to keep those malformed events for later investigation. And in that case, we have what is called a dead letter queue. And a dead letter queue or DL queue is basically, as it sounds, it's just a queue. And this queue just used to store all the bad and all the malformed requests of our services that they may receive, and just to have for us to later use that. Some stateless services perform a retry mechanism when their compute part throws an exception. We'll deep dive to that retries in a few slides. But what's important to understand is that a retry mechanism does not differentiate between a malformed input or a temporary error. And this just can cause serious bottlenecks if our system doesn't have any dead letter queue implemented right. Also, a few stateless environments already have a built-in DL queue capability, and I'll just we can just check them in the next slide. So Amazon SNS, the simple notification service, as a built-in DLQ, where a Lambda function, every time it gets invoked, it might fail. So every time it fails a certain amount of time, it can be sort of like circuit breaked into a DLQ. And think about it, that all the notification that are being sent to that Lambda function, if it failed, if it recurrently fail and doesn't succeed even after a few retries, we can just take those events and put them in a DLQ. We can store them into S3 and just have our engineers to investigate that queue on a later time. This can help us build a much more resilient service that will not go out of services due to a single customer or malformed input. And if our services will not recover from malformed input, that is not fixable if we perform a retry mechanism, this service will become our application's bottleneck. So we can just use middleware to assist us in identifying such issue, and we can also see the true effect of it just by looking at some metrics. And one of the metrics is called an iterator age, and an iterator age is probably the best metric to look at when you're trying to figure out whether you have bottlenecks on your stream-based stateless environment. And I think it's the most used metric to identify bottlenecks in those stream-based stateless environments. And it actually just shows the age of the oldest record being processed by our service, meaning that a large iterator age can be due to various of reasons. The main one is, in this case, of malformed input that's causing a recurring error or just a slow processing time. Where we handle high scale, but our compute service is slow and can't handle the load. Basically the case where our input rate is much larger than our output rate. There are some ways to actually improve the slow processing, specifically in Lambda function. And the first way is just by simple configuration change. And I'll show that right in the next slide. But what's also important to understand about iterator age is that the longer it is, the more that there are going to be delays in the system. So taking that seriously will really significantly improve the overall experience of all your customers, and also the actual time that actually been in those services. And by improving and doing those configuration changes in the Lambda function, you can also improve the time that it takes to process, even if you are not changing the code. And not a lot of people actually know this, but setting up the memory size of a Lambda function directly affects the performance of the Lambda, meaning that memory affects both network and CPU ticks allocated to the Lambda. And what we did is that we built a simple application. It's running a Fibonacci series, and we try to test the same code over and over again with different configurations. And that's exactly what we did. So the chart just shows an average duration of the application changes where the memory actually increases. And it also has an effect on the CPU and the network share. So due to that effect in the network share, when your application Lambda calls an HTTPS, because of the SSL certification and the SSL handshake, we also detected that it's required to have at least 512 megabytes in order to just get an improved performance. And other than then, doing all of this benchmark, you can see that the more memory you're going to use, the more it's going to be, the performance is going to be improved. And in some cases, also in terms of pricing, you can use more memory, but because you improve the performance time, in Lambda function, you're going to pay less. So you can take, we put this utility tool benchmark that we built. We also made it open source. So you can just go to our repository, Epsagon's repository, and just plug your Lambda function, and it will run a benchmark and give you the best assumptions of the memory configuration. And so these are just some of the ways to overcome errors. The most common ones to overcome errors are actually retries. And I want to just take you back to the 90s where we get this screen. I'm pretty sure all of us are pretty much familiar with that. And this is like back in the days, we got that a lot. And it was always in some important game, or we were playing, or some multiplayer game, or maybe just writing some important document. And something just broken in our operating system, and the only way to actually solve it was by simply just keeping calm and trying again and actually resetting the computer. And the same goes for stateless environments. Because they are stateless, retrying makes sense. So we can just try to run it again because maybe it doesn't have any access to the database, but running it again might be effectable. And a retry mechanism is probably one of the most useful tools to overcome errors in the stateless environment, and it is implemented by many services today. Let's first discuss what is a retry mechanism. And a retry mechanism can either be synchronous or asynchronous. And a synchronous retry meaning that we have an application that is failing, but the responsibility of actually calling it again is under the caller. So think of an HTTP request I'm sending to an endpoint. If the endpoint will actually return 400 or 500, I can call it again with the same parameters, but expect different results. So asynchronous retry is the case where a vendor or service has a built-in retry mechanism and is not triggered by the user. For example, a stream-based service that is failing with a particular input will get retried a few times again and again with the same input, and this time the mechanism controlled by the service itself. It's also fully configurable, and you can set the retry configuration in Lambda. You can also drill down into specific configurations such as the minimum delay or maximum delay, or even just decide the type of backup function, whether it's linear or exponential. And we just touch a little bit about what exponential is right now. So exponential backup is a pretty common backup function. Every time we have an exception, we like to retry, but if we keep a constant rate, we might require much and more retries. So just using exponential backup means that we gradually try to find that sweet spot and the right rate and actually changing the time exponentially. As it can be seen on the chart, it reduces the average transmissions needed significantly, but does spread over much more. So SNS uses that as default, by the way, and I think the most important thing when it comes to retries is actually being aware of them. So in Epsagon, we've implemented retry detection that will allow you to see every execution that was part of the same retry attempt. You can see all the attempts and access each one of them. Each attempt has a different effect on your system, and it's super critical to be aware when it happens so you can have much more clear troubleshooting process. But other than just troubleshooting, you need to build your application to be retry aware. It needs to be idempotent. So idempotency is basically the practice of identifying repeated events, meaning that our service is currently in the second or more retry attempt, but responding accordingly, meaning that either fail gracefully or making sure we don't damage our application. So retry can be very destructive to our application. And this is just an example of an application where we receive customer requests to perform a payment. And if our service will fail again and again, it will be reinvoked with the same customer data, we are taking the risk of charging the customer again. So the first thing we need to make sure is that we terminate the code gracefully, so we will not have to charge it again. But a much more stronger method will be to actually introduce a state to that stateless service just by storing session data. And it just sounds intimidating at first, but it's pretty easy, specifically when using DynamoDB or a key value database, that everything is fully managed. So our database can store the state of our request, or every request, its state will be initially stored in that database. And our service just need to fetch that state data and update it before and after the execution, meaning that after every call, we store the current state. And yes, that's the perfect use case for middleware, and it can become much pretty useful to actually use that. So you can just create, each time there is a request, create a new record in the database and keep fetching that information, so you will not have to worry about if there's going to be a retry that you will also do some perform to other services. And so the last topic I would love to talk about is distributed tracing. And stateless environments are very much distributed in their nature. And this has changed the way we monitor our application. There's a whole new challenges team are actually facing today in their microservices environments. and we can just check them out one by one now. So the first thing is that stateless environments or modern cloud-based apps or microservices can be very problematic for engineers and DevOps in terms of observability. And the more things become much more distributed, the more it's become very hard to understand what's actually going on within. So unfortunately for engineers and DevOps, building, monitoring, and troubleshooting cloud microservices is not just straightforward as saying, okay, we need to move to the cloud, we can save on costs. It requires much more work to just gain that ability to troubleshoot and also monitor those distributed systems. And you need to know whether the application is working properly, how to enable developer velocity, what's currently running in production to rapidly build new cloud services and save on development costs. And that's basically what distributed tracing is coming to actually solve. So let's a little bit discuss what it is and why is it actually critical today. So troubleshooting production issues for microservice and serverless are requiring much more than just the basic logs and metrics, which are simply not the right tools for these highly distributed applications. And each component in our system can report back every time it runs with all the operation that it did. So putting that into an engine that is able to correlate between different events will eventually allow us to view a full picture as like an end-to-end request like you see here, or simply just see an end-to-end trace. And a trace, meaning that it's the story of all the services that were invoked and how a single request propagated through that distributed system, meaning I have a customer and he has sending a request that goes through 4 or 5 different services. So being able to see all the journey, and sometimes it can be much more complicated than that, and also asynchronous, so also be able to capture all those together and then view them and see exactly what's going on within them. There's a lot of open source tools to enable distributed tracing in your code. There's a standard like open tracing, and there's also Jaeger, which is an open source distributed tracing, which also has a timeline view that you can visualize those traces. But how can we actually implement that ourselves? So first, we need to instrument every call in our service, meaning that whether it's a call to the S3 using the AWS SDK or a record being put to the database or any other third-party API call, for every call we create a span. A span should contain all the information needed for operation, the host name, the duration, and much more high-level metrics. And a distributed tracing engine needs to know to connect between those asynchronous spans using correlation identifiers. So we need to ingest and extract those identifiers. It can be the request ID. It can be anything that is very unique to a specific request or response. And as for the context, we would like to add much more request-specific data to assist us with troubleshooting, such as this is just an example of how to manually implement those distributed tracing in a single request. So we have our handle request function, and before the request, we put it into create a span for it with all the context. So the example of the context can be the URL or the remote IP or the caller name, any data that will actually allow us later on looking at the trace and being able to properly troubleshoot it. So in Epsagon, we took all this idea of implementing automatic tracing libraries that require you almost zero code changes in a way that you just plug in the library and it will automatically detect all the operation that's going on, just to reduce the fact that a developer will need to manually annotate and add spans. And so this is part of our tracing library. Also, our SaaS offering for the observability solution, specifically built for cloud microservices, we provide value to those complex environments immediately, rather than just needing to manually define spans or run separate engines to collect metrics for serverless components. Epsagon automatically traces the end-to-end state of your services and providing application insights and metrics with visibility into the payload. You can check us out later. So just to summarize, errors in a stateless environments can and will happen. We just need to be able to identify them and prepare for them. One of the main technique is retries, which is a very powerful method. of just overcoming errors, but also requires to implement it right. And lastly, distributed tracing is the key to gaining full observability into distributed systems, and it's a crucial component in stateless environments. So thank you, guys. And I'd also like to share that you can just go to epsagon.com/allthetalks and get a free swag. It's our cool, nice T-shirt. So thank you, guys. Thanks you guys so much.
Awesome. Thank you very, very much, Hen. So a couple of questions coming in, one which I will ask directly. The other one I'm going to pull in our next speaker so he can ask live on the stream. So we have MHMXS asking regarding about storing state. How do you deal with storing state and business logic that are happening as two separated flows, two separated steps, and the fact that errors can exist between those two steps?
So I think it's not that easy task of containing the state. You will need to have some sort that database need to contain access from both services, and they both can have joint states. You just need to make sure that you will handle those atomic operations, so you will not be able to overrun them. Mm-hmm. But once it comes to adding more and more services that need to have a shared state, meaning that you might need to contain them in a single service or try to figure out a different way to communicate between them.
Awesome. And let me pull in Ramiro. Welcome, Ramiro, to All the Talks. How are you?
Hi, I'm good. How are you, Simon? Hen? That was a great talk.
Hi.
Thanks for that. I have a question, so I'm going to ask it live, which is something we've been hitting a lot of lately is we're in the process of implementing open tracing, and some of the services we're calling in our chain of services, legacy stuff that does not support open tracing or open telemetry. What should we do in those cases? Like I have my API calling login that works with open tracing. Then for instance, they call Kubernetes, has no support for this, and then we call some other APIs downstream. What do you do?
Yeah. So I think the differentiator between what is supported and not supported in open tracing is rather the environment. It's more the actual programming language, because you can manually, I think it, unless it's like C++ or anything, I think maybe for C++ they also have a support for that. So you just need to figure out a way. And open tracing is just basically the standard. You can manually create those spans within your code. And if you decide to do the manual way, and you basically need to transmit that to the open some tracing engine as well. So I would love just to even hit that offline with you to see how we can assist with that.
Yeah, sure. Thanks.
Awesome, and I'll give Ramiro a full introduction in just a second. But while we continue on the questions, one more question coming in from Slido, from Joe. Is there support for traces over hybrid architecture? So, for example, from going from a container to a serverless architecture?
Yes, definitely. So when it comes to Epsagon, our automated tracing library is agnostic to where the code runs. So it can run on containers or Kubernetes, on serverless and all that. So you can also see requests going from invoking a Lambda function that putting a message on S3, invoking a Lambda function to calling an endpoint on the Kubernetes itself. So you can see all the end-to-end trace, even in hybrid systems.
And using something like Epsagon, would you say it's like a always-on kind of solution, or would you say it's like as and when you feel like you need to do more investigation, you turn the trace run?
Yeah, so we have our own monitoring system that you can decide when you want to actually plug it in or plug it out, but it also brings an overall infrastructure monitoring. So it's always on in a way, but it's fully agentless, so you just collect metrics remotely. Awesome.
Hen, we're at time now, so I will say a massive thank you very much for the session. Thank you very much for
thank you so much. I had fun.
And Epsagon support as well for all the talks, and we appreciate your coming on. So thank you very much, and enjoy the new day, I guess, in Tel Aviv. Miro is ending up his in San Francisco. So have a great rest of the day, Hen. Thank you.
Thanks. You too, guys.